Welcome back to the 7th installment of my series on Earth's extinction events. Today we're diving into one of the most iconic periods in our planet's history, the Jurassic, the age of the dinosaurs. Compared to the chaos of the Permian and Triassic, the Jurassic was relatively calm. After the 4th largest extinction event ever, life bounced back in a big way. That recovery gave rise to some of the most famous animals to ever walk the Earth. Dinosaurs that have captured the imagination of kids and adults alike since they were first described in the 1800s. If you're new to this series, don't worry, this video stands on its own. But if you're curious about earlier mass extinctions, check out the full playlist. If you're interested in exploring this topic more yourself, I've linked a document in the description listing the sources and image credits that I used. Let's set the scene for this dynamic chapter in Earth's history. A time when lush forests covered the land and oceans teemed with bizarre giants. The Jurassic lasted for about 58 million years, from around 201 to 143 million years ago. The climate was warm, there was no ice at the poles, and temperatures were stable. Jungles flourished and vast plains, not the arid deserts of the Triassic, were alive with activity. This was the golden age of the sauropods. Massive, long-necked herbivores like Brachiosaurus lumbering in herds across the plain. Alongside them were armor-backed stegosaurs and early forms of ornithopods like Dryosaurus and Lesothosaurus, primitive versions of what would later become dominant during the Cretaceous. In the skies, pterosaurs ruled, mostly from the group Rhamphorhynchoidea, known for their long tails and sharp maneuverability. Their wings were built for darting through the air, not soaring long distances. While Pteranodon often steals the spotlight, it actually came much later during the Cretaceous. In the Jurassic, more modest pioneers of powered flight, like Pterodactylus, were just beginning to evolve. Beneath the waves, marine reptiles dominated. Streamlined ichthyosaurs sliced through the waters like prehistoric dolphins, while plesiosaurs diversified, some with long necks for snatching small prey, others like Leopleurodon, built like torpedoes to take down bigger game. The latter Suchians, early crocodile relatives, were also making a splash, fully adapted to life at sea with paddle-like limbs. Meanwhile, early sea turtles began moving from freshwater to marine habitats, and it's not just reptiles. Ammonites, belemnites, bivalves, gastropods form the backbone of marine ecosystems. Coral reefs, devastated in the end Triassic extinction, were recovering, with scleractinian corals, the same kind that build today's reefs, starting to dominate. Even crinoids and brachiopods, former ocean royalty, were still hanging on, though no longer in their prime. And what about the plants? Forget flowers, fruit, or even grass, those didn't exist yet. The Jurassic landscape was dominated by gymnosperms. Conifers, cycads, and ginkgos towered overhead. Below them, ferns and horsetails covered the forest floor. Flowering plants wouldn't show up until the Cretaceous, making Jurassic flora a strange pre-bloom world. Now that we've painted a picture of Jurassic life, let's zoom in on something less well known, a minor extinction that almost slipped through the cracks of history. For this, let me give you a little peek behind the scenes. I actually stumbled across this one by accident. I was wrapping up the script when a single line in a Wikipedia article, of all things, caught my eye. It mentioned the Gibbosus event, something I'd never heard of throughout the rest of my research. And if you haven't heard of it either, you're not alone. There's no standalone Wikipedia page and barely any research, probably because it was followed closely by the much more famous Toarcian Oceanic Anoxic event. But the Gibbosus event is fascinating in its own right. It occurred around 184 million years ago and was likely triggered by global cooling. While small in scale, it had a serious impact, especially on ammonoids, a group of shelled cephalopods related to squid and octopuses. Named after Ammonitis gibbosus, this event wiped out 70 to 90% of ammonoid species. The survivors were far less diverse, which is clearly reflected in the fossil record. Shell shapes narrowed dramatically after the event. Other marine groups were probably affected too, bivalves, brachiopods, maybe even plankton, but it's hard to say for sure, since many of those groups were also hit hard by the Toarcian event shortly afterward. Some paleontologists even wonder if the Gibbosus event was an early phase of the larger extinction that followed, a sort of warning tremor before the main shock. While that's an interesting idea, the prevailing view is that it was a distinct, smaller-scale extinction, a precursor, not a part. Either way, it reminds us that not all extinction events are dramatic apocalypses. Some, like the Gibbosus event, are quiet and easy to miss, but they still shape the evolutionary story of life on Earth. Just 1,000,000 years after the Gibbosus event, Earth was hit by another, much more dramatic extinction, the Toarcian Oceanic Anoxic event. Now, the name might make you think this is just another marine crisis, but it went way beyond that. Life in the ocean suffered the most, yes, but land ecosystems were shaken too. This event occurred around 183 million years ago in the early Jurassic. It actually had two main pulses, sometimes treated as separate events. Technically, the first is known as the Plensbarkian-Toarcian boundary event, and the second is the Toarcian Oceanic Anoxic event proper. But from everything we know, both were likely caused by the same trigger, so for this video, we're treating them as one continuous crisis. At the start of this time period, Earth actually cooled, forming thin ice sheets that reached surprisingly far towards the equator. This might sound strange given what we said earlier about the warm Jurassic climate, but remember, this was a brief exception, not the rule. Then came the turning point, a sudden spike in global temperatures caused by massive volcanic eruptions. These eruptions, part of the Karoo igneous province, pumped out vast amounts of carbon dioxide, causing CO2 levels to double in a short period. This rapid warming melted what little ice there was and triggered a cascade of environmental disasters. Sound familiar? Many scientists see this event as a deep time warning for modern climate change. Different causes, same pattern. A sudden carbon spike and global consequences. So, how does carbon dioxide actually cause warming? CO2 is a greenhouse gas. It traps heat from the sun in our atmosphere. This natural effect keeps Earth warm enough for life, but when levels change too quickly, it disrupts the balance. In this case, the result was a temperature spike of 3 to 7 degrees Celsius in the oceans, depending on the latitude. At its peak, the average ocean temperature hit 21 degrees Celsius or 70 Fahrenheit. Compared to today's 16 degrees Celsius or 60 Fahrenheit, that may not sound extreme, but for marine life, it was devastating. The heat wasn't the only problem. Oceans began to lose oxygen, anoxia, and some regions became euxinic, meaning low oxygen combined with toxic hydrogen sulfide. Euxinia was mostly confined to the northwest Tethys Ocean, but where it occurred it was catastrophic. Hydrogen sulfide disrupts ecosystems, poisons organisms, and binds with toxic metals like iron and uranium. At the same time, ocean acidification spiked. At first there was a drop in acidity, caused by volcanic rock weathering. That released basic compounds like carbonates into the sea. But as CO2 kept rising, it began to dissolve into the oceans, forming carbonic acid, pushing acidity levels back up fast. Other processes made things worse. For example, less oxygen meant less burial of organic carbon, which increased carbon buildup in the oceans, intensifying acidification. The result? A deadly cocktail. Hot, acidic, oxygen-starved, hydrogen sulfide-rich seas. The hardest hit were the marine invertebrates, especially those with calcium-based shells or skeletons, because acid dissolves calcium. Brachiopods suffered their worst extinction in over 500 million years. Nearly 90% of species vanished. One resilient genus, Soaresrinkia, managed to not only survive but actually thrive, thanks to its slow metabolism and low oxygen needs. That genus is sometimes credited with single-handedly preventing the entire phylum from going extinct at this time. Ammonites, already reeling from the Gibbosus event, lost 50 to 70% of their remaining species, leading to a full evolutionary reboot of the group. Ostracods, tiny, tough crustaceans that shrugged off past extinctions, weren't so lucky this time. 30 to 50% went extinct, mostly near the equator. They quickly rebounded, but it's one of the few times they were significantly affected in Earth's history. Bivalves saw mixed results. Some lineages collapsed under Anoxia, others were relatively unscathed. This varied response was likely a result of their tolerance to Anoxia. Some could cope, while others could not. Corals and reef builders were devastated. Up to 90% of reef-building species vanished, likely due to acidification, which also caused a domino effect on reef-dwelling organisms. Marine vertebrates handled the crisis better, mostly thanks to their higher mobility. Ichthyosaurs and plesiosaurs declined slightly in some regions, but didn't suffer a mass extinction. Fish populations shifted regionally, with some local disappearances, but again, there was no global die-off. On land, the volcanic activity triggered deforestation, wildfires, acid rain, and soil erosion. Conifers and other gymnosperms declined temporarily, giving way to early colonizers like ferns, before reclaiming their dominance again later in the Jurassic. In the animal kingdom, there was turnover among dinosaurs. Early sauropodomorphs declined, while true sauropods, the giant long-necked dinosaurs, began their rise. Small theropods, like Coelophysis and Dilophosaurus, were replaced by larger predators that would dominate later Jurassic and Cretaceous ecosystems. Other dinosaur groups also began to evolve rapidly around this time, suggesting that the Toarcian extinction cleared ecological space, allowing new lineages to emerge and diversify. The Toarcian Oceanic Anoxic event didn't just cause extinction, it reshaped ecosystems, altered climate systems, and redefined evolutionary trajectories for millions of years to come. Our last extinction event of the Jurassic period takes place right to its very end, the Tithonian Age, roughly 152 to 145 million years ago. But here's the twist. It wasn't really a mass extinction. Not in the dramatic, world-ending way we've seen before. Instead, it was more of a gradual transition, a faunal turnover where old lineages slowly faded out, and new ones quietly took their place. The exact causes of the Tithonian transition are still debated. The leading theory? Cooling climates, which may have triggered a small-scale glaciation causing sea levels to drop. That, in turn, shrank the shallow seas many marine animals depended on. Other possible culprits include volcanic activity or local anoxia. Unlike the widespread oxygen loss of the Toarcian event, any anoxic conditions here were likely regional. Marine invertebrates again took the brunt of it. Groups like ammonites, corals, sponges, bivalves, and brachiopods, all invertebrates with low mobility and reliant on shallow marine habitats, were significantly affected. These were the same vulnerable players we saw in earlier crises. We don't have a clear record of what happened to the land plants. There are signs of regional turnover, especially among conifers and cycads, but the scope is still uncertain. What we do know is that any change in vegetation would have rippled up the food chain, altering the diets, habitats, and survival chances of the herbivorous dinosaurs that depended on them. There was definitely a shift in dinosaur dominance, even if the fossil record of this time is not well documented. Stegosaurs began their decline. They survived the Tithonian but would be extinct by the early Cretaceous. Meanwhile, Silurian saurian theropods, the group that includes tyrannosaurs, dromaeosaurs, and even birds, started to diversify rapidly. For the sauropods, the Tithonian was a major turning point. Familiar groups like Diplodocids, Macronarians, and Mamenchisaurids suffered major losses. A few held on to the Cretaceous, but the real successors were the Titanosaurs, who would go on to be the last great sauropods, being the only sauropods to survive to the end of the Cretaceous. Pterosaurs were also undergoing big changes. By the end of the Jurassic, most non-pterodactyloid pterosaurs had vanished. Groups like the long-tailed rhamphorhynchoids declined sharply, while the pterodactyloids, more advanced and diverse, rose to dominance. One reason might be the emergence of birds. Early birds were smaller, more agile, and may have outcompeted their pterosaur counterparts. That could explain why the most iconic Cretaceous pterosaurs, like the giant Asdarchid Quetzalcoatlus, filled roles that birds hadn't evolved into yet. Still, this wasn't just about competition. Many extinct pterosaurs were large piscivores or open ocean gliders, roles birds didn't yet fill. So the decline of these pterosaurs was likely the result of many factors. The seas were also changing. Ichthyosaurs, already declining since the mid-Jurassic, were hit hard. A few lingered into the Cretaceous, but the group never fully recovered, and would vanish entirely by the mid-Cretaceous. The Latasuchians, those marine crocodile relatives, faced a similar fate. Once diverse and widespread, they saw a sharp drop-off in the Tithonian, and were gone shortly after. But not all marine reptiles struggled. plesiosaurs and pliosaurs adapted and diversified, staying successful well into the Cretaceous. So, with all this change, surely there was a definitive extinction event that marks the end of the Jurassic, right? Well, not really. In fact, the Jurassic is unique among all periods in Earth's history. It has no formally defined ending. No single event, no boundary layer, just a slow transition. That transition saw some lineages decline and others emerge, but those patterns had been happening throughout the Jurassic already. The Jurassic-Cretaceous boundary is usually placed at around 143 million years ago, but honestly, that's almost arbitrary. What really changed? Let's start with the dinosaurs. Theropods remained the top predators, but the Cretaceous carnivores were a different breed. Allosaurs, ceratosaurs, and megalosaurs faded, replaced by tyrannosaurs, carnotasaurs, and feathered dromaeosaurs like Velociraptor and Utahraptor. Some, like Therizinosaurus, even took bizarre evolutionary paths. Despite its ridiculously long claws, it swapped meat for plants and became a herbivore. Herbivores changed too. Stegosaurs disappeared, and sauropods shrank in diversity, with only titanosaurs remaining. In their place, new players rose to prominence. Hadrosaurs, ceratopsians, ankylosaurs, and pachycephalosaurs, many armed with horns, clubs, or armor. The Cretaceous also saw flowering plants, angiosperms, make their debut. These would gradually replace Jurassic conifers and cycads, reshaping terrestrial ecosystems forever. And in the skies, pterosaurs evolved into giants, while birds flourished in the niches of small aerial hunters. As continents continued to break apart, ocean circulation improved, spreading nutrients more widely. That gave rise to new marine giants. Pliosaurs and ichthyosaurs faded. The plesiosaurs held on for a while longer before giving way to new predators. This led to the rise of mosasaurs, giant aquatic reptiles more closely related to lizards than they are to ichthyosaurs or plesiosaurs. The end of the Jurassic didn't come with a bang, but a slow, steady transformation. You might notice that most of these lineages didn't end with the Jurassic. They persisted into the early Cretaceous. This is why the date of 143 million years ago for the end of the Jurassic is almost arbitrary. It was a time of faunal turnover, climactic shifts, and evolutionary innovation. From the ashes of old lineages, new ones arose to define the Cretaceous, perhaps the most iconic chapter in Earth's history. I hope you enjoyed this video. The Jurassic was an incredible time in Earth's history, full of evolutionary drama, extinction, and adaptation. From the peak of the stegosaurs and ichthyosaurs to the early rise of birds, coelurosaurians, and flowering plants, it set the stage for everything that came next. Next time, we'll be back with a classic video on a very odd group of aquatic moles. But when we return to this extinction series, we'll be diving back into the Cretaceous and working our way toward the most famous mass extinction of all time. Until then, thanks for watching, and let me know in the comments what you'd like to see covered in future episodes.